Thank you very much. So I'm very happy to have this chance to present you this research. The research is done in collaboration with people at Humboldt, but actually now some of them moved. So they are Lorenzo Bianchi, which is now in DESY Hamburg, Marco Stefano Bianchi, which is now at Queen Mary in London, and then Björn Leda, who's the director of our computing center, and Eduardo Vescovi, who's going to graduate in 1 month here, and Philip Töpfer, who's just a master's student, but already working very well. So, some motivation. So, there is a beautiful progress already for some years in obtaining exact results within AdS CFT. So, results for which various functions are known exactly, so implicitly or explicitly as a function of the coupling. And so not only in the regimes which are naturally under control, like perturbative gauge theory, so see an expansion in powers of G. So G will be our only coupling, so I define it here. It's the square root of lambda, and it's given in this way in terms also of the effective string tension. R square is the radius of AdS 5 and S5. We will be dealing with this, the most important version of AdS CFT. So not only in the perturbative regime of gauge theory and the perturbative regime of string theory, which goes in the inverse power of G, inverse powers of the tension, but also in between. And the ways we know how it goes in between are basically two: either integrability or supersymmetric localization. However, not only integrability in this finite region of the coupling is just assumed, and supersymmetric localization only works by definition for protecting observables, but also from the point of view of string theory, of the Worldsheet theory, integrability is a solid fact classically, well, with several evidences of quantum integrability, but these are evidences, and the localization is not even formulated. It still waits for a formulation from the point of view of string theory, of the string worldsheet. So superstrings in AdS backgrounds with Ramon-Ramon fluxes are still field theory models which are very complicated, highly interacting, and which are basically under control perturbatively and with some caveats. You might have had a look at a poster of Eduardo Vescovi, and by the way, what I'm talking about was already presented in a poster by Philip Töpfer on Monday afternoon. So, it is a natural question to ask whether there is a method, which actually it's a first principle method, genuine QFT method, to look at this finite coupling region. And we know already for some times, for some years, in this framework, there are various attempts in the framework of AdS CFT, but particularly relevant here is the study is putting n equal 4 superior Mills on the lattice, so the 4-dimensional gauge theory. And this is an exciting program, which is, however, quite complicated. The subtleties are related on how to put supersymmetry on the lattice, and there is a basic control only in the perturbative region. I will have some comment about this at the end of the talk. Today I'm going to talk about how to put the string theory worldsheet on the lattice in AdS 5 cross S5. There is an important paper which was written in 2013, which is our main inspiration, and it's by Royban and his student, McEwan. And although, in fact, we are also able just to cover the perturbative region with some evidence for non-perturbative behavior, there are many attractive features which make this study an interesting project, which are also from the lattice point of view, which are that of course if you work in 2 dimensions, this must be computationally cheaper than working in 4 dimensions. But importantly also, since we work with the Green-Schwarz formulation of the superstring, we do not have supersymmetry on the 2-dimensional world. We also gauge fix kappa symmetry, and we actually gauge fix everything. So another simplification is the fact that we do not have to introduce plaquette or link variables. Everything here is given in terms of scalar fields, some of which are anti-commuting. So this is a an interesting theory actually on its own, even beyond our community, hopefully, because it's a non-trivial, highly non-trivial two-dimensional field theory, for which, highly non-trivially, there is an analytic strong coupling expansion. Here, strong coupling, from this point of view, of this part of the diagram, strong coupling means weakly coupled n equal 4 super Mills, which is analytically known, and also there is a finite coupling prediction. So these are all non-trivial things which makes this study worth to do that. So I'm done with the motivation and will continue presenting the model that was under our study and its discretization, and also, of course, I will deal with simulations and the continuum limit of them. And since there will be a problem emerging in this third point, I will give just a sketch of a proposal of an alternative setting for dealing with it, unfortunately without simulation, and then I will conclude. Okay, so the observable that we are going to study, since it's a novel study, or the second study in this framework, it's something which is completely known, completely solved via integrability. It's the best studied observable, one of the best studied in AdS CFT and certainly in the framework of integrability, and it's the Cusp anomaly of n equal 4 super Mills as seen from string theory. So it's this coefficient here, which appears multiplying this double divergence, this one. So it's a pure function of G, and it governs the renormalization of a Cusp, the Wilson loop. This phi, so in the Euclidean plane, this is the Cusp. It's big phi, and this small phi is its analytic continuation, which is taken to take the Minkowski limit and to actually have the definition of the light-like Cusp. So in string theory, what you do is to take the partition function of the string and create some boundary conditions so that the string will end on this Cusp and resum over all the fluctuation above and around this classical solution. So it's a calculation of a partition function with certain boundary condition. Actually, this minimal surface, the classical solution around which perturbation theory is done in a semi-classical expansion, is this one. So in Poincaré patch, is this ansatz here, is this surface in terms of z, x plus, and x minus. This is the conformally flat form of the AdS metric, AdS5 cross S5 metric, and the fact that makes this the correct classical solution is that at the boundary of AdS5, where z is 0, x plus is 0 or x minus is 0. So it's a good candidate, and in fact it has been used to study in semi-classical quantization the partition function. What happens is actually that this solution is so nice that it can create a factorization Lagrangian with constant coefficient. So in fact one can proceed by simply Fourier transforming, and in fact what one finds is a factorization of V2, which is an infinite dimensional, an infinite volume, the two-dimensional volume, and which is the stringy counterpart of this divergence that is circled here. So these are numbers that most of you know very well. I emphasize 3 log 2 because we are going to make, actually to really derive it with our discretization, and it is an important test of our work. But, so normally one would evaluate effective actions, partition functions, but in a lattice approach, one prefers to evaluate webs of operators. And so, what is meaningful to do in this context is to try to find a way to get information on the Cusp via a web. And a natural way is to take the web of the action, of the fluctuations around the Cusp, which is given in terms of a logarithmic derivative of the partition function, because you see G appears factorized in front of the action. If you derivate with respect to G, you bring down the Lagrangian, multiply by G, you get the action. But since you are doing the logarithmic derivative, you also get down, actually not the Cusp anomaly, but its derivative. So we are going to have information on the derivative of the Cusp anomaly. Okay, so webs in lattice QFT are evaluating through a certain procedure, which I recall. So first of all, we need to set some names. So we are going to discretize our space-time using a lattice spacing, which is a real number constant, A. It's a square lattice, although the temporal direction will be taken always double, because we are going also to study correlators. And this is good because you want to actually have a good exponential decay, so large in time. And the lattice, as we know, provides a natural regularization in that all the momenta are constrained to be set into the first Brillouin zone, but also provides us with a definition of the path integral measure, because also in our case in particular, all scalar fields are sitting at the lattice sites, at the nodes, so that the path integral becomes actually a multidimensional integral, and then the lattice partition function, which is this multidimensional integral where the weight of the action is now a Euclidean action, and where the continuum derivatives are replaced by finite differences. This lattice partition function becomes statistical systems with the degrees of freedom which your theory has, and they can be studied through Monte Carlo simulation, which means that you generate a number of configuration, so an ensemble, which is a sort of snapshot of your field content at all the lattice sites for all the degrees of freedom. Each of these field configuration is weighted with a certain probability, which is this Boltzmann weight normalized. And then to define a VEV, you are going to take, so this is just the definition, the continuum definition, you are going to take this average. And of course, the more configuration you can generate, the better is the approximation. It's actually exact for an infinite number of configuration, which is why 2 dimension is better than 4, because the algorithm which generates fields in this case scales like n square. We are in 2 dimensions. If you have Grassmann fields, you can't generate them easily. So what you do is usually either completely forget about them. These are the so-called quenched approximations. Or you formally integrate them out, so you try to define a determinant of them, and you include them in the weight. So to do this, obviously, you need to have fermions which are at most quadratic, because you want to define the determinant, and typically, of course, in string theory, we don't have this situation. But in our case, we have a gauge-fixed action. It is the AdS lightcon, which is at most quartic in the fields. So it's pretty easy to do the linearization. In fact, it's always easy. You just have to introduce as many auxiliary fields as you want. And you get, in turn, these Yukawa terms, which, of course, enter the quadratic fermionic operator. Also, to enter the probability, this determinant must be definite positive, otherwise cannot be interpreted as a probability. And therefore, if you have a determinant, you substitute it with this quantity here, which is obviously not equivalent, but it's definite positive. And then what you do is to re-exponentiate this in terms of something that you can actually generate, so bosonic degrees of freedom. These are the so-called pseudo-fermions, complex bosonic degrees of freedom. And you see here this minus 1/2, so the inversion of this squared fermionic operator is one of the most difficult things to do. It's actually the crucial part of the algorithm. In our case, we will have a Pfaffian, so it's slightly modified. We have a 1/4 here, minus 1/4 here. Well, and still I want to emphasize that this substitution is useful for the simulation, but of course it neglects potentially very important information like the presence of complex phases, the presence of anomalies, and so on. Okay, so the model in the continuum from which we start with is the action for the fluctuations around the null cusp, which was written down in this paper, and it's this action here, which is still quartic in fermions, and let me describe the field content. We have, as expected after gauge fixing, 8 bosonic coordinates, the ones which are transversal to the worldsheet, the physical one, which are a complex scalar field, X and X star, and which are 7 other scalar fields comprises in this vector Zm. So Zm are this comprises actually the radius of AdS and the 5 coordinates of S5. So we have also 8 fermionic complex variables which have lost their spinor indices. Now they are just complex anti-commutating fields, theta I, and also there is a theta I which is conjugated like this. You change the index, and eta I. And they transform in the fundamental representation of SU4. Also, you see these row matrices, which are the off-diagonal block of SO6 Dirac matrices, and there are also row Mn, which are the related generators of SO6. So, as I said, there are still quartic fermionic interactions. This one underlined that you want to linearize, and this is the very natural linearization, is a Gaussian integration. And this is what you will deal with, and this is what you will end with. So here, this is the Lagrangian after linearization, where the first line is basically the same. You see I have underlined, I've emphasized, highlighted this M, which usually you don't find in the articles. And actually it's just a P+, which if you do analytic calculation, you always set to 1. But from this perspective of putting things on the lattice, you can't disregard any dimensionful parameter, which appears as a bare parameter in the action, because it's in principle subject to renormalization. So this is the linearized. So you see you have you have this quadratic fermionic operator, which is this monster here. And it's a 16 by 16 matrix. Now there is a formal variable which comprises all the fermionic degrees of freedom. I call it formal because it's redundant, so it has the theta I and eta I, but also the complex conjugate. So if you want, it respects a sort of Majorana conditions, and that's why indeed you have psi transpose and not the conjugate, and that's why you have a Pfaffian of this operator and not a determinant. So the operator is this one, 16 by 16, and this A are the Yukawa terms which are introduced by the linearization. So this is still the continuum, and because now we want to discretize, we want to have some criteria to do a good discretization, the first of which is that at a certain level in a lattice perturbation theory, we want to reproduce the continuum limit. So just a sketch of what happens in the continuum at one loop. To reproduce the 3 log 2, you take the free kinetic part of the fermionic operator in Fourier transform, which gives this determinant contribution. This goes in the denominator, well, it goes because there is an M, a minus. In the numerator, you have the determinants of the bosons, and integrating, so we said we can Fourier transform, the solution is so-called homogeneous, so there is all the translational symmetry that you want, and you get this 3 log 2 multiplied by V2. Now, usually you can try to proceed naively, and if you look at the 2-point function of fermions, the naive way, I think also this is well known, to replace a continuum momentum is to replace it with this sinus here. But this also naively and directly leads to fermion doublers. It can be checked, namely that this determinant is actually having the same values at 4 points, not just 1, so 4 points 2 to the t, and the other 3 points, the ones which are not the physical fermion, are so-called doublers, and they are a lattice artifact. But the point is that they remain in the continuum if you don't do something special. And the something special which is done, which it's actually very well known in QCD, is to add a term in the Lagrangian, which is typically an irrelevant term. So it's proportional to A, but in the continuum limit, A is the lattice spacing and has to go to 0 in the continuum limit. In the continuum limit, this term is such that it makes decouple all the unphysical doublers. And so we add it following this order of importance. So lattice perturbation theory should reproduce the continuum counterpart. Actually, they are equally important, these points. Also, the discretization should be not such to introduce some problems in the setting. So the way to ensure no problems is not to get additional complex phases. I already anticipated there is a complex phase in the game, but the way we proceed with discretization is to set, for example, the auxiliary field to 0 and to see whether what we get is something good. Something good means that the determinant of this new fermionic operator with the Wilson term is real and non-negative, and this is what happens, and also very important that the global symmetry is preserved. And here I realized that I didn't emphasize enough at this level that this Lagrangian in the continuum has a manifest global symmetry which is SO6 times SO2. SO6 is because, well, the solution is not, and the gauge fixing are not touching the isometries of the sphere. SO2 is also because there are two directions which are transverse to the classical solution in which you are free to actually rotate, and these are the X fields. And all the fields have charges with respect to these symmetries. So they have to be ideally maintained. So we can't maintain the SO2, but we maintain the SO6. We can't because there is a sort of no-go, at least we don't find it, of no-go theorem. So we actually add this Wilson term to the fermionic operator. It's given in terms of p hats, which are good in the sense that the Brillouin boundaries, they do not diverge, they are finite, but this combined with what they are multiplied for, here this 1 over a actually makes the decoupling of the doublers. So this discretization is good because it reproduces the 3 log 2. You see, this is the integral with this momenta translated in this way, and if you take the continuum limit, this is what you get. So we get this V2, but also M square, well, everything should be dimensionless. And this is the Cusp anomaly of strong coupling. So again, it preserves the SO6, but it breaks the SO2. I anticipated, actually, we tried with another discretization, which breaks everything, but results seems not to be sensitive to this. Okay, so now let's go to simulations. So first of all, one has to specify the parameter space. So the bare parameters that you give as an input to the computer should give you out the physical observables. So in the continuum model, there are two bare parameters, which are the dimensionless coupling G and the dimensionful parameter M. We have seen, I recalled the easy calculation that in perturbation theory, actually, suppose everything, divergences are supposed to cancel always, and dimensionless quantity will be pure function of the bare coupling. On the lattice, we have checked just now that discretization, at least at one loop, cancels the divergences because it reproduces the 3 log 2. And so we assume that this happens non-perturbatively, which means that we think about not counter terms to add, but just the additional scale natural in this setting, which is the lattice spacing. So we have to deal with the three-dimensionless parameters. They have to be dimensionless to be input to the computer. G, the number of lattice points, and this big M, which is a dimensionless combination in which the massive parameter appears. So the observable on the lattice will be a function of these three parameters. Now, very important is to define the way that the continuum limit is taken. So you can't, in principle, just create a continuum limit sending the lattice points to infinity, although more or less is what we do. But you have to do that in a controlled way, and the controlled way is actually dictated by the renormalization property that physical quantities should not depend on the scale, and so they should be kept constant when the scale varies. So these are the line of constant physics. They are curves in the bare parameter space where dimensionless physical quantities, so typically the renormalized quantity, are kept fixed as the scale changes. So what are the physical quantities which is natural here to keep constant are the masses of the excitations over the cusp, which were studied by Benjamin Bassot and by also perturbatively by these guys. And here I just report the perturbative calculation. I will show later the diagram of Benjamin and Pedro and Sever. And this is how it behaves in the continuum. So there is a finite renormalization occurring, so quantum corrections. And so if we want to create a dimensionless, so to be kept constant, it has to be dimensionless. We multiply the left-hand side by the lattice size L square to create something dimensionless. So this means that we multiply also the right-hand side. And if we assume that the coupling constant is not renormalized, so G is not renormalized as it happens in the continuum, and this is a mild assumption, which is basically also made, for example, in n=4 super-Yang-Mills on the lattice, we get this line of constant physics, which is these two parameters, big N and big M, kept constant. Of course, to have a meaningful way to proceed, we have to check that this is true. So this line of constant physics must be true, so this relation should be true, or at least should not receive corrections in an infinite renormalization also on the lattice, and this is what we are going to check. So, but to rephrase the continuum limit, what we expect is that our observable of the lattice in the continuum limit, which I'm going to define now explicitly, gives the continuum observable plus finite lattice spacing effects. So if there are no infinities coming out, plus finite volume effects. The finite lattice spacing effects are 1 over n or order A, clearly. And the finite volume effect, well, you can think about this combination is actually M, like the mass parameter times L. So it's multiplied together. This is like the number of Compton waves which fill the box of the lattice. If it's big enough, the degrees of freedom should not fill the boundaries, and you want to do that. You want that your finite volume effects are small. So the recipe to take the continuum limit will be to fix G, well, to have our simulation done, and then to take the continuum limit will be to fix G, fix this Mn, and large enough so that the finite volume effects are small, are under control, evaluate a flat for various values of the number of lattice spacing n, and obtain the continuum observable, extrapolating for an infinite number of lattice points. So the first measurement that we do, we call it really a measurement, it is a measurement, is to check that actually this line of constant physics is meaningfully taken. So we want to check that the mass of these X fields is actually not undergoing an infinite renormalization. We do that extracting it from the correlator of the X fields. So this is the correlator where it's already partially Fourier transformed actually, and the momentum is taken to 0. So this is the meaning of this sum, is a Fourier transform only in the spatial direction, and then the spatial momentum is taken to 0. It is known that this combination here is actually a sum over states of different energies that in the limit of large temporal extent is approximated by the state of lowest energy, which for a spatial momentum to 0 is the definition of the physical mass. So we extract actually the physical mass, so the mass of this excitation on the lattice, actually via a limiting procedure which uses the effective mass, which is this discretized logarithmic derivatives, which also get rid of this constant here that is difficult to determine. So the correlator is this one, exponential decay. This here is actually the effective mass over m square. What we are happy about is that you already see it goes at 0.5, 1/2, which is precisely, is precisely this 1/2 appearing here. Okay, here. And, but of course I can show you the continuum limit, and you might not like it, but we sort of like it. First of all, because the perturbative region is still good, so it's consistent with this 1/2. And of course here there are a lot of errors, but we still, so it's not really clear that it will bend down to go like the curve, the prediction in the continuum, the curve by integrability is going down. So, however, from the point of view of what we wanted to check, so whether there is an infinite renormalization occurring, this is still good. And since we see large errors here, I want to comment, and also something that could be really made better if we had longer runs and if we had parallelization, for example. I want to make immediately a comment on the numerics, because I already emphasized this is a simple model, two-dimensional, only scalar fields, no supersymmetry, and so you would expect really something very good going on. However, there is so it's still string theory, so it knows it. And in fact, the most difficult part of the algorithm for everyone is the inversion of the fermionic matrix, as I already said. So this is again, so this is the weight, so the way the fermionic degrees of freedom participate in the whole study is via this weight, which is this re-exponentiation requiring the inversion. Now, the algorithm that we use is very standard, is a Monte Carlo algorithm hybrid, which means that it mixes a random approach, so randomly generated field configuration are then evolved through an Hamiltonian in a fictitious time. It's very standard, and the important word here is rational. So you have to give a rational approximation of this fractional power here. And what one does is to rewrite this in terms of this partial fraction expansion. And here, this coefficient alpha 0, alpha I, and beta I are given by an algorithm, which is called the Remes algorithm. And you just need to give as an input the range of the eigenvalues of the operator and the precision, which is if you want how many terms this sum has, and then it outputs these parameters. But the inversion comes now is the solving of this system, where Si is defined like this thing appearing here. So the inversion happens here. What you give is this zeta, the pseudo-fermion, randomly generated. Beta I are there. Here there is an identity matrix. It's a linear system. You give OF, and you get this inversion Si. So the point I want to make here is just that there is a solver, there is an iterative algorithm to do this, which is called the multi-shift conjugate. And this algorithm has a number of iterations which are necessary to get the convergence of these equations, which goes like lambda min to the -1, where lambda min is the minimum eigenvalue which is contained in this fermionic operator. And in our case, the spectrum of the fermionic operator is not bounded positively from below, so it can get arbitrary small eigenvalues, and plus, just to zoom one of the entries of the operator, which I didn't emphasize enough before. So this is certainly, to see fields appearing in the denominator and highly fluctuating, this is certainly exotic, at least from the point of view of Lattice experts. So there are difficulties, and that's why things are not going smoothly. Measurement 2 is the observable that we want actually to get the information on, is the Cusp anomaly, or better, the derivative of it. How do we do that? Here I recall the continuum prediction. We know already that f prime of g, for example, at large g should be this 4 here, and we just translate in terms of our input parameter. So this is what we would expect. But on the lattice, what we see emerging are quadratic divergences. So divergences because there is a coefficient here multiplying n squared that in the continuum limit we go to infinity. This coefficient, you can extrapolate it. It's actually an extrapolation of S over n squared. Here you see we added a log of g just to make more visible these curves. So I tell you what it is. It's 7.5 at large g. You see it very well here. at large G is 7.5, which is 15 over 2, which is the number of bosonic degrees of freedom over 2, which is a good explanation because what happens is that in lattice codes, the coupling constant does not multiply the fermionic part of the action, the pseudo-fermionic part of the action, but it only multiplies the bosonic degrees of freedom. So at large G, you see just an action which is quadratic in bosons multiplied by G. You can evaluate it either by rescaling or just explicitating the determinants. And so you will have a power of G to the number of degrees of freedom which are bosonic in front of everything. And since you take the logarithmic derivative, this C, this thing here is sort of expected. But the point is that the divergences appear also at finite G. So you could have expected, because this is the same plot on the last slide, and it goes on, this evaluation of C. It is a function actually of G, so it's something bad. Divergences are always bad, but, and you see that here. So I want to, let me just say that this plot on the left is the action where we subtracted the first constant contribution, so the 7.5 that I emphasized before, and you see at large G is good, we get a 1. 1 is what we expect to get at large G for the derivative of the cusp with these factors in front. But then this behavior is clearly divergent. You can't see very well all the curves, but these are the ones for smaller G, the one which diverge more. Okay, so this is how you can actually calculate this constant. I call it constant, but I made a mistake because this is a function of G. And if you have the question how you can separate these two contributions, which is a legitimate question, well, you can, because these extrapolations are done dividing everything by n squared, because you want to determine the coefficient. And since here, this thing is precisely that the product which is kept constant in the way we take the continuum limit, this divided by n squared and taking the n to infinity goes away. So you can isolate this C, and you can give a measurement for it. So we shouldn't forget that we see divergences, but we see also divergences in perturbation theory in the continuum. There, in fact, one uses, in this setting, with the same Lagrangian that I've shown, truncated to the various order, one uses usually dimensional regularization to get rid of them. So power divergences are just thrown out of the window. There is also another way in which one could understand this, the emergence of this divergence. It was suggested by a discussion with lattice experts, which have the same problem in studying another part of the action, which is the gluon condensate. Trace of S squared is just a Yang-Mills action, so it's still an effective action, or an action. Evaluating the level width, they see quartic divergence. And this is so, quartic is 4 dimension, quadratic is 2 dimension, so you can think about it like in mixing terms, like the mixing of the Lagrangian, which is dimension 2 here, with lower dimensional operator with the same quantum numbers, and here would be with the identity operator. So the dimension of this operator here would be 0, the identity, and you would have a to the minus 2, which is a quadratic divergence. Okay, so how do we proceed? Well, in dimensional regularization, you throw divergences. On the lattice, which is a cutoff regularization, you can proceed in various ways, probably the roughest of which is what we do. So we could study better this thing, but this is sort of standard. One can proceed subtracting divergences. Usually this is very bad because you have errors subtracting divergences which are potentially terrible. They could diverge when you take the continuum limit. But what I want to emphasize is that in our case, this seems a nice procedure because, so what I show here is the subtraction of this C2 times n squared. So in principle, we could still see divergences, but if you suppose that they are quadratic, they are completely subtracted. And this is why everything goes smooth here. Also, you see the errors. So the continuum limit is going from right to left. You see the errors are not growing. So this is a justification for which the this subtraction works well. When you see multiple points, these are multiple replica, which is just a simple way to do parallelization, the simplest way. So we can then extrapolate at infinite n. So we go on the extrapolation to the continuum limit is going again from right to left to show the continuum limit. And this is our measurement for the derivative of the Cusp anomaly. So here you see the perturbation theory curve is drawn, is done. So these points here, you should remember that we are looking at the derivative of the Cusp. So it's not the Cusp. So in fact, the derivative of the Cusp, doesn't see the 3 log 2. It sees the Catalan constant and it goes upwards. Unfortunately, we are not able to see this upward trend. But we are pretty happy, but let me describe how we do this comparison. So in principle, the coupling on the lattice and the coupling on the continuum may be different. So there could be something which causes a renormalization. And so the way we proceeded is to fix one point, which is not predictive, and it's this where it lies precisely on the continuum curve. And the other one is the prediction. So we fix, we suppose that there is a rescaling, finite rescaling between the couplings. We match the lattice measure for f prime to the continuum prediction, and from this we extract this relation, and we plot the measure in terms of the continuum G. Okay, you see, we coupling, good. This thing, not so good, but still you see the bending. So now I will have a comment on this, why the bending is still good. But let me say something. It could be that this rescaling is not actually, this finite rescaling is not, there is not a simple relation, it's non-trivial, which would take out completely the predictivity from the measurement, but also, well, to see this, we should measure things here, lower in G. We can't because there is a phase. I anticipated this problem. It's introduced by the most natural linearization, which gives you a sort of the wrong sign in the quartic fermionic interaction. This B is a bilinear in the fermions, so this is a quartic interaction. And you see this Gaussian, you can get it just by introducing B is Hermitian and I. Okay, so the phase is not a bad problem in principle if it can be somehow treated. And the way one treats it is to take it out from the, of course, from the probability, from the weight, and to insert it as an observable. This is the so-called reweighting procedure, which gives, however, meaningful result as long as the denominator is not zero, and also the numerator is not highly oscillating, which means that the phase should not average to zero, otherwise we have the famous sign problem. And you see we have it. So we have it, so at large G, it's fine. These are histograms which calculate which show the number of configurations for which the real part of the phase is measured. The imaginary part of the phase is zero, as it should be. We are still measuring an observable, so we do not expect an imaginary part, but the phase, remember, has a real part, and this is the problem here. Now, we could take this as something positive, like, okay, we have a problem for which we know the continuum prediction. We can study it with alternative algorithms, which are an active field of study because there is no general proof of convergence. But there is, I want to show a proposal of an alternative setting. There is something that can be done analytically. Unfortunately, it's not everything, but something can be done. And it's very nice, so I want to show it. So this is a simple example of four fermion interaction with S of 4 invariants that we write simply like this. These are anti-commuting scalar variable, so fermions, but they are not spinors. There is this epsilon tensor. So you can actually introduce in these bilinears, which are bilinears in fermions, which are different, of course, and sigma tilde, which is the dual, and you can rewrite the four fermion interaction in this way. Then you introduce a self-dual, another combination of this sigma and sigma tilde, and anti-self-dual, sigma plus or minus, and you can rewrite, look, plus or minus this thing here. So you can sort of decide the sign if you then, of course, if you then linearize in terms of auxiliary field, which must be real, the auxiliary fields are introduced and they have to have a real support to be useful, because you have to then generate them randomly with the computer. So this thing, I hope you see, maybe not, my handwriting, is just going backwards just to convince you that you have this plus or minus, which looks like an ambiguity, but is in fact the epsilon tensor that has this ambiguity inside. So the thing is that one can apply this to our problem, where this is the sign that we don't like. And you can use the algebra of the row matrices, which gives you an epsilon tensor, to do the same construction, and I'm fast here, and you see this minus plus appearing here. And now you choose the good sign, and you linearize again, and now you eliminate at least the problem of having a Lagrangian which is not Hermitian. So you have now a full non-negative determinant of the operator. Unfortunately, we have a Pfaffian, not a determinant, so we still have a plus or minus ambiguity, so you could say, okay, you trade the phase problem with a sign problem, properly said, a plus or minus ambiguity, but this is still good because of numerics, because if you have to calculate, if you have to do reweighting with the phase, you have to calculate the phase. And the calculation of complex determinants is always a bit nasty, so it requires, at least it scales like n6 in this case, so the size of the matrix times to the 3, the third power. So the good trade is for the reweighting, and simulations are ongoing. Unfortunately, I don't show you anything, but there could be an improvement. Well, there is for sure expected an improvement. So before the concluding remarks, I just want to, for curiosity, to show you what happens with the best result that is now got on the CFT side. So this is from the Lattice conference that was in July in Southampton. David Scheich is in the group of Catterall, that you might know maybe better, is a postdoc. He will come to Bern in September. And this is just to show, so this is the coefficient of the Coulomb behavior of the quark and anti-quark potential, the way you define it in A=4 superior Mills, and the way you define it on the lattice, which is by a suitably constructing Wilson loop. So you go to the large T, and you measure, and they are happy because they find it Coulombic as expected from the conformality of the theory. But also what I want to emphasize is that they do a control, and this is the best result that they have, with the next to leading order perturbation theory. And actually I talked to David, and he told me that, okay, they can't distinguish between leading, next to leading, and so on, because, well, the coupling is very small. You see also they have a rescaling, but here there is a geometric origin. It's sort of a Jacobian between the continuum coordinates and the discretized coordinates, and since there is a 1/g² in front of the action, there is also this Jacobian, so it's like a redefinition of the coupling. Okay, so also they have a sign problem, a strong coupling. Of course, there is no expectation that they should be in any way related to our problem, but okay, this was just to say something about the other side. So the conclusions are that we ask ourselves whether we could use standard methods of lattice QCD, for example, to study Green-Schwarz gauge fixed strings on the lattice after the study of Radu-Roypan. And the answer is yes. We adopted Wilson-like fermion discretizations to different ones, and results seem not to be sensitive to this. We used standard simulation algorithms. There is a good agreement with coupling, and we see that this is, however, also the situation on the other side. And there is also a qualitative agreement. On the other side, there is not. They don't see any bending with the non-perturbative expectation from AdS CFT. As small g, we detected a complex phase, and there is a proposal of an alternative setting. There is an important comment, which is I already made, that in principle, if there is a non-trivial rescaling between the couplings, you don't have any prediction, but still you can do then something, in the sense that you can take this measure of a function of the coupling as your renormalized coupling. You can tune the parameters, and then you can really measure, this time in a predictive way, something else, which would be in our case the mass. And so there is a lot of future, because this is just the beginning. So simulations with alternative realization, correlators, but also different backgrounds, for example, the ones relevant for the VGM Cusp. But of course, there is one thing to be said, that this is not a universal setting. Every time we have to change the Lagrangian, because it's gauge fixed. So in the future, there is also, together with further observable, and so with gaining something in predictivity, but of course, until we don't see very well how to recover something well known, one tends not to do something else. So in the future, there could be also a better formulation of string theory on the lattice, but that's a very open problem, because so what to use as a gauge field, it's not clear, at least to me, to us. Thank you for your attention.
Thank you very much, Valentina. There is time for some short questions.
Can we also study a spectrum of excitations when
I have shown the correlator of the X fields, and I said that in the future there is the study of the other correlators, and I re-show you the result is this one. So it's not completely nice as compared to the prediction, but well, at large G is okay. And then there is some problem. For the masses, at least for this correlator, it's not so trivial. So the future will be other correlators.
And instead of ABGM, probably you can just do ABG Cusp.
Sure. That's what I meant.
One last question from Ben.
I'm just curious what kind of computer resources went into these computations.
Okay, so for the moment, it's like there is a pool here at Humboldt, so everyone is running things from the laptop. So the computer resources, well, are just simple. So there is not yet any parallelization, and so yeah, it's the pool of the Humboldt. So it's like a simple way of parallelizing is just to get multiple runs with the same parameters and from all the collaborators. So no special core hours. Well, yes, it's a bit long, but yeah, like something like I think it's 1 week minimum. Yeah, unfortunately, but yeah, for simple runs. Yeah.
So, in view of time, I would